Explain vulnerability management. Lesson Introduction. Vulnerability management is critical to any organization's cybersecurity strategy, encompassing identifying, evaluating, treating, and reporting security vulnerabilities in operating systems, applications, and other components of an organization's IT operations. Vulnerability management may involve patching outdated systems, hardening configurations, or upgrading to more secure versions of operating systems. For applications, it might include code reviews, security testing, and updating third-party libraries. Vulnerability scanning is a crucial component of this process, with specialized tools utilized to identify potential weaknesses in an organization's digital assets automatically. These tools scan for known vulnerabilities such as open ports, insecure software configurations, or outdated versions. Post-scanning, analysis is performed to validate, classify, and prioritize the identified vulnerabilities for remediation based on factors such as the potential impact of a breach, the ease of exploiting the vulnerability, and the importance of the asset at risk. This continuous cycle of assessment and improvement helps organizations maintain safe and secure computing environments. Lesson objectives. In this lesson, you will do the following. Describe the importance of vulnerability management. Explain security concerns associated with general and application-specific vulnerabilities. Summarize vulnerability scanning techniques. Explain vulnerability analysis concepts. Rate your confidence. Device and OS vulnerabilities. Exam objectives covered. 2.3 Explain various types of vulnerabilities. Operating systems, including mobile operating systems, are a common target for cyberattacks. Managing vulnerabilities in these systems plays a central role in cybersecurity operations. Vulnerabilities are introduced from various sources, such as flaws in the operating system's design, errors in its code, or unsecured default settings. Attackers can exploit these vulnerabilities to gain unauthorized access, disrupt operations, or steal sensitive information. Additional concerns arise in mobile operating systems due to factors like the diversity of devices and operating system versions, bypassing operating system protections, and using apps downloaded outside official app stores. Identifying and managing vulnerabilities often involves keeping operating systems updated with the latest patches, hardening system configurations, carefully managing user privileges, and controlling software applications. Rate your confidence. Operating system vulnerabilities. Operating systems, OS, are one of the most critical components of any infrastructure, so vulnerabilities in an OS can lead to significant problems when successfully exploited. Microsoft Windows has an extensive feature set and broad user base, especially among large organizations and governments. Its vulnerabilities often include buffer overflows, input validation problems, and privilege flaws typically exploited to install malware, steal information, or gain unauthorized access. Windows is an important target for attackers because of its large install base. Large corporations and governments heavily depend upon it, which compounds the significance of its vulnerabilities. Apple's macOS vulnerabilities often stem from its Unix-based architecture, and weaknesses generally appear in access controls, secure boot processes, and third-party software. Apple macOS has a smaller user base than Windows, but its popularity has grown significantly. Generally, macOS is perceived as being safer than other operating systems, which can lead to complacency. Linux is a prevalent server OS, but can also be used as a desktop or mobile OS. The open-source nature of Linux and the large community of active developers support a very rapid pace of development. This generally results in quick identification and repair of vulnerabilities. Kernel vulnerabilities, misconfigurations, and unpatched systems are common issues in Linux. Despite its reputation for security, its widespread use in the cloud and server infrastructure makes Linux vulnerabilities especially significant. The widespread adoption of mobile OS like Android and iOS and their increasing use as primary computing platforms instead of traditional computers make them valuable targets for attack and exploitation. Android is open source, like Linux, resulting in similar benefits and problems. Additionally, Android OS is fragmented among different manufacturers and versions, resulting in inconsistent patching and update support. iOS, while not open source like Android, has also been impacted by several significant vulnerabilities. The significance of OS vulnerabilities cannot be overstated, especially as specialized embedded systems, such as IoT, are added to our surroundings. Each system runs specialty operating systems and introduces vulnerabilities and potential pathways into corporate infrastructures. Example OS vulnerabilities. Microsoft Windows. One of the most notorious vulnerabilities in Windows history was the MS08-067 vulnerability in Windows Server Service. This vulnerability allowed remote code execution if a specially crafted packet was sent to a Windows server. This vulnerability was exploited by the Conficker worm in 2008, which infected millions of computers worldwide. Additionally, MS17-010 represents a significant and critical security update released by Microsoft in March 2017. This update addressed multiple vulnerabilities in Microsoft's implementation of the Server Message Block (SMB) protocol, a network file sharing protocol that could allow remote code execution (RCE). Essentially, these vulnerabilities, if exploited, could allow an attacker to install programs, view, change, or delete data, or create new accounts with full user rights. The significance of MS17-010 is tied closely to the Eternal Blue exploit, which leveraged the vulnerabilities in early versions of the SMB protocol for malicious purposes. The most famous misuse of Eternal Blue was during the WannaCry ransomware attack in May 2017, where it was used to propagate the ransomware across networks worldwide, leading to massive damage and disruption. This event underlined the critical importance of timely system patching and reinforced the potential global impact of such vulnerabilities. macOS. In 2014, a significant vulnerability called shellshock affected all Unix-based systems, including macOS. It allowed attackers to potentially gain control over a system due to a flaw in the bash shell. Though it originated from a component in Unix systems, its impact was felt in macOS due to its Unix-based architecture. Android. The stage fright vulnerability discovered in 2015 is a prominent example for Android. It allowed attackers to execute malicious code on an Android device by sending a specially crafted MMS message. This issue was particularly severe due to the ubiquity of the vulnerable component, the stage fright media library, across Android versions and devices. iOS. In 2019, Google's Project Zero team discovered a series of vulnerabilities in iOS that nation-state attackers were abusing. These watering hole attacks took advantage of several vulnerabilities to gain full access to a device by having the victim visit a malicious website. Linux. The Heartbleed bug in 2014 was a severe vulnerability in many Linux systems' OpenSSL cryptographic software library. The vulnerability allowed attackers to read the system's memory running the OpenSSL software's vulnerable versions, compromising the secret keys used to protect data. Rate your confidence. Vulnerability types. Legacy and end-of-life (EOL) systems. Hardware vulnerabilities, particularly those associated with end-of-life and legacy systems, present considerable security challenges for many organizations, as patches or fixes for vulnerabilities are either unavailable or difficult to apply. End-of-life, EOL, and legacy systems share a common characteristic: they are both outdated. EOL systems may be legacy systems, and some legacy systems are also EOL. The manufacturer or vendor no longer supports EOL systems, so they do not receive updates, including critical security patches. This makes them vulnerable to newly discovered threats. Conversely, while still outdated, the vendor may still fully support legacy systems. An EOL system is a specific product or version of a product that the manufacturer or vendor has publicly declared as no longer supported. It is also possible for open-source projects to be abandoned by the maintainers. An EOL system can be a hardware device, a software application, or an operating system. Products should be replaced or updated before they reach EOL status to ensure they remain supported by their vendors and receive critical security patches. Notable EOL product examples include the Windows 7 and Server 2008 operating systems, which stopped receiving updates in January 2020. These systems are significantly more vulnerable to attacks due to the absence of security patches for new vulnerabilities. Despite their EOL status, they are still in use in many environments. Many devices, peripheral devices especially, remain on sale with known severe vulnerabilities in firmware or drivers and no possibility of vendor support to remediate them, especially in second-hand, recertified, or renewed/reconditioned marketplaces. Examples include recertified computer equipment, consumer-grade and recertified networking equipment, and various Internet of Things devices. Legacy systems typically describe outdated software methods, technology, computer systems, or application programs that continue to be used despite their shortcomings. Legacy systems often remain in use for extended periods because the organization's leadership recognizes that replacing or redesigning them will be expensive or pose significant operational risks stemming from complexity. The term legacy does not necessarily mean that the vendor no longer supports the system, but rather that it represents hardware and software methods that are no longer popular and often incompatible with newer architectures or methods. Legacy systems often remain in use because they operate with sufficient reliability, have been incorporated into many critical business functions, and are familiar to long-tenured staff. Assessing the risks associated with using EOL and legacy products, such as lack of updates, lack of support, and compatibility issues with newer systems, is crucial. EOL and legacy product replacements must continue to meet the organization's requirements, maintain compatibility with existing infrastructure, and support reliable data migration. Selection criteria must consider the availability of vendor support, device warranty details, and marketplace performance/reputation. Transitioning costs must be carefully assessed, too, including licensing, hardware upgrades, and professional service implementation fees. The work to transition away from EOL and legacy products must minimize disruptions and ensure long-term sustainability. Firmware vulnerabilities. Firmware is the foundational software that controls hardware and can contain significant vulnerabilities. For instance, the Meltdown and Spectre vulnerabilities identified in 2018 impacted almost all computers and mobile devices. The vulnerability was associated with the processors used inside the computer and allowed malicious programs to steal data as it was being processed. Another vulnerability, LoJax, discovered in the Unified Extensible Firmware Interface, UEFI, firmware in 2018, enabled an attacker to persist on a system even after a complete hard drive replacement or OS reinstallation. End of life, EOL. Hardware vulnerabilities arise when manufacturers cease providing product updates, parts, or patches to the firmware. Virtualization vulnerabilities. While offering numerous benefits such as cost savings, scalability, and efficiency, virtualization also introduces unique vulnerabilities. A significant one is the concept of VM escape. This happens when an attacker with access to a virtual machine breaks out of this isolated environment and gains access to the host system or other VMs running on the same host. Such a vulnerability could allow an attacker to gain control of all virtual machines running on a single physical server, leading to a potentially devastating security breach. A famous example is the Cloudburst vulnerability in VMware's virtual machine display function. The Cloudburst vulnerability, officially designated as CV 2009-1244, was a critical security flaw discovered in 2009 in VMware's ESX server, a popular enterprise-level virtualization platform. A vulnerability in the virtual machine display function allowed a guest operating system to execute code on the host operating system. Another significant vulnerability associated with virtualization involves resource reuse. Virtual machines are frequently created, used, and then deleted in a virtualized environment. If the resources, such as disk space or memory, are not properly sanitized between each use, sensitive data could be leaked between virtual machines. For instance, a new virtual machine may be allocated disk space that was previously used by another VM, and if this disk space is not properly wiped, the new VM could recover sensitive data from the previous VM. Thorough data sanitization practices, ensuring data encryption throughout the lifecycle, and implementing robust encryption key management practices mitigate the risk of resource reuse in cloud infrastructure. Training on cloud provider security features and best practices and segregating resources based on security levels also mitigates risks. Virtualization platforms depend upon specialized hypervisors that contain security vulnerabilities and weaknesses. Attackers exploit hypervisors to gain unauthorized access and compromise the virtual machines, VMs, running on them. Hypervisors typically provide specialized management interfaces so administrators can control and monitor their virtualized environments. These interfaces can become potential attack vectors if insecure. For example, weak authentication, lack of encryption, or vulnerabilities in communication protocols can lead to unauthorized access to the virtualized environment. Like any software, hypervisors have vulnerabilities that must be regularly patched. Zero-day vulnerabilities. Zero-day vulnerabilities refer to previously unknown software or hardware flaws that attackers can exploit before developers or vendors become aware of or have a chance to fix them. The term zero-day signifies that developers have 0 days to fix the problem once the vulnerability becomes known. These vulnerabilities are significant because they can cause widespread damage before a patch is available. An attacker exploiting a zero-day vulnerability can compromise systems, steal sensitive data, launch further attacks, or cause other forms of harm, often undetected. The stealth and unpredictability of zero-day attacks make them particularly dangerous. They are a favored tool of advanced threat actors, such as organized crime groups and nation-state attackers, who often use them in targeted attacks against high-value targets, such as governmental institutions and major corporations. Since these vulnerabilities are unknown to the public or the vendor during exploitation, traditional security measures like antivirus software and firewalls, which rely on known signatures or attack patterns, are often ineffective against them. The discovery of a zero-day vulnerability typically triggers a race between threat actors who aim to exploit it and developers who work to patch it. Upon discovering a zero-day vulnerability, ethical security researchers usually follow a process known as responsible disclosure, which is designed to privately inform the vendor so a patch can be developed before the vulnerability is publicly disclosed. This practice aims to limit the potential harm caused by discovering a zero-day vulnerability. The term zero-day is usually applied to the vulnerability itself, but can also refer to an attack or malware that exploits it. Zero-day vulnerabilities have significant financial value. A zero-day exploit for a mobile OS can be worth millions of dollars. Consequently, an adversary will only use a zero-day vulnerability for high-value attacks. State security and law enforcement agencies are known to stockpile zero days to facilitate the investigation of crimes. Misconfiguration vulnerabilities. Misconfiguration of systems, networks, or applications is a common cause of security vulnerabilities. These can lead to unauthorized access, data leaks, or even full system compromises. These can occur across many areas within an IT environment, from network equipment and servers to databases and applications. In a cloud environment, misconfigurations, such as improperly managed access permissions on storage buckets, can lead to significant data leaks. Default configurations of systems, applications, or devices are often designed to prioritize ease of use, setup simplicity, and broad compatibility. However, this often results in a security trade-off, making these defaults a common source of vulnerability. For instance, default configurations may enable unnecessary services that open potential attack vectors or include easily guessable default credentials, such as admin for both username and password. Some systems may have overly permissive configurations that heavily focus on usability and potentially expose sensitive information if left unmodified. Network devices like routers and switches often have default configurations that compromise security, such as well-documented default credentials and the use of vulnerable management protocols. Similarly, cloud services often have default settings that leave data storage or compute instances publicly accessible. Administrators and engineers must carefully configure systems, devices, and applications according to the principle of least privilege and published best practices. This includes changing default login credentials, tightening access controls, and regularly auditing configurations to ensure ongoing security, as a minimum. Providing support to resolve functional issues in an IT environment is an essential part of maintaining business operations, but it can also inadvertently lead to misconfigurations and vulnerabilities. For example, while troubleshooting an issue, a support technician may temporarily disable security features or loosen access controls to help isolate a problem. If these changes are not reverted after the issue is resolved, they may leave the system vulnerable. Similarly, installing new software or modifying existing software configurations can introduce unexpected vulnerabilities or leave the system less secure. Remote support tools can also pose a risk if not adequately secured, and an attacker could exploit these tools to gain access to a system or network. When addressing urgent issues and outages, especially high-impact ones, best practices for change management are often bypassed. Changes are made without proper documentation, testing, or approval, leading to misconfigurations or system instability. Cryptographic vulnerabilities. Cryptographic vulnerabilities refer to weaknesses in cryptographic systems, protocols, or algorithms that can be exploited to compromise data. The significance of such vulnerabilities is profound, as cryptography forms the backbone of secure communication and data protection in modern digital systems. Moreover, weaknesses in cryptographic algorithms themselves can also pose a threat. For instance, MD5 and SHA 1. Once widely used cryptographic hash functions are now considered insecure due to vulnerabilities that allow for collision attacks, where two different inputs produce the same hash output, which is particularly troubling in scenarios where hashes are used to protect passwords. Practical examples of cryptographic vulnerabilities include the Heartbleed vulnerability, which exploited a flaw in the OpenSSL cryptographic library, allowing attackers to read otherwise secure communication. Another example is the crack key reinstallation attacks, vulnerability in the WPA2 protocol that protects Wi-Fi traffic. This vulnerability allows an attacker within range of a victim to intercept and decrypt some types of sensitive network traffic. Symmetric and asymmetric encryption algorithms and cipher suites can also have vulnerabilities that lead to potential security issues. One of the most significant vulnerabilities in symmetric encryption algorithms is the use of weak keys. The Data Encryption Standard (DES) algorithm, once a popular symmetric encryption standard, was found to be vulnerable to brute force attacks due to its 56-bit key size. The DES, developed in the early 1970s, was first publicly demonstrated to be vulnerable to brute force attacks in the late 1990s. This led to its replacement by more secure standards such as Triple DES and eventually the Advanced Encryption Standard (AES). Triple DES, 3DES, which applies the DES algorithm 3 times to protect data, was considered significantly more secure than DES when it was initially introduced. However, with the continued advancement of computational power and the discovery of additional attack methods, 3DES vulnerabilities have been found, most notably the Sweet 32 birthday attack, CV 2016-2183, published in August 2016. The U.S. National Institute of Standards and Technology, NIST, officially deprecated 3DES in 2017 and recommended its discontinuation by 2023. Some asymmetric encryption algorithms also have vulnerabilities. For instance, RSA, a widely used public key cryptosystem, can be vulnerable if small key sizes are used or if the random number generation for creating the keys is weak. Also, if the same key pair is used for an extended period in an asymmetric scheme, the likelihood of the key being compromised increases. Cipher suites, which describe combinations of encryption algorithms used in protocols like SSL/TLS, can also have vulnerabilities. SSL/TLS is commonly used to secure web browser sessions, encrypting communication between a browser and a web server and essentially turning an HTTP web address into a secure HTTPS address. SSL/TLS is also used for secure email transmission, SMBP, POP, IMAP protocols, secure voice over IP, VoIP, calls, and file transfer protocols secure FTPS. In all these cases, SSL/TLS helps protect sensitive data from being intercepted and read by unauthorized parties. Other networked applications and services also use SSL/TLS, including VPN connections, chat applications, and mobile apps that transmit sensitive data. Prominent examples of attacks against Cypher Suite vulnerabilities include the Beast, browser exploit against SSL/TLS, and Poodle, padding Oracle on downgraded legacy encryption, attacks that target weaknesses in the Cypher suites used by SSL and early versions of TLS. Both attacks exploited similar implementation flaws. Protecting cryptographic keys. Generating and protecting cryptographic keys is crucial for ensuring the security and integrity of sensitive information. The most robust cryptographic system is rendered useless if the keys used to protect it are weak or poorly guarded. Kirchhoff's principle establishes that a cryptosystem should be secure, even if everything about the system except the key is public knowledge. Cryptographic key generation describes the process of creating cryptographic keys for encryption, decryption, authentication, or other uses. It is important to use industry best practice approaches when generating cryptographic keys to ensure they cannot be guessed or brute forced. Cryptographic key protection requires implementing specialized security measures to safeguard keys from unauthorized access or disclosure, as cryptographic keys are typically nothing more than strings of alphanumeric characters stored in simple text files. Common secure key storage practices are secure key storage systems, such as hardware security modules, HSMs, or key management systems, KMS, implementing proper access controls and authentication mechanisms, and regularly monitoring and auditing key usage. Additionally, organizations must periodically change cryptographic keys, also referred to as key rotation, to strengthen the system and combat risks associated with key breaches and brute force attacks. Rate Sideloading, rooting, and jailbreaking. Mobile devices introduce unique security vulnerabilities related to their operation, specialized software, ubiquity, and ability to store and collect vast amounts of personal and professional data. Rooting and jailbreaking are methods used to gain elevated privileges and access to system files on mobile devices. This allows users to bypass certain restrictions imposed by the device manufacturer or operating system. Rooting involves gaining root access or administrative privileges on an Android device to modify system files, install custom ROMs, modified operating system versions, and access features and settings not available to regular users. Jailbreaking describes gaining full access to an iOS device, iPhone or iPad, by removing the limitations imposed by Apple's iOS operating system. Jailbreaking allows users to install unauthorized apps, customize the device's appearance and behavior, access system files, and bypass restrictions implemented by Apple. The practice of sideloading applications refers to installing applications from sources other than the official App Store of the platform, such as Google's Play Store for Android or Apple's App Store for iOS. While sideloading allows for greater software flexibility and choice, it poses significant risks as sideloaded apps do not undergo the same scrutiny and vetting process as those on official app stores. This makes it easier for malicious apps to be installed, potentially leading to data theft, privacy breaches, and other issues. Additionally, apps that require excessive access permissions can raise significant security and privacy concerns. App permissions should align with the app's purpose. Apps with excessive permissions may access sensitive user data without a legitimate need, including personal information, corporate data, contacts, call logs, location data, or device identifiers. Granting unnecessary permissions to apps increases the device's attack surface and the potential for security vulnerabilities.
Description.
The menus at the top are Apps, Forum, Docs, News, Issues, Contribute, and About. The text below reads, "What is F-Droid?" F-Droid is an installable catalog of FOSS, free and open-source software applications for the Android platform. The client makes it easy to browse, install, and keep track of updates on your device. A button on the left reads, "Download F-Droid" with a PGP signature link at the bottom. Below the link is a QR code. A smartphone screen shows the icons for 2048 Puzzle Game, Terminal Emulator for Android, Wikipedia, Antenna Pad, Barcode Scanner, and Contact Messenger. The menu at the bottom reads, Latest, Categories, Nearby, Updates, and Settings. The F-Droid Android Application Store. Screenshot courtesy of www.opensecurityarchitecture.org. Rooting, side-loading, and jailbreaking offer users greater control and flexibility over their devices, but they also introduce many risks for organizations. Rooting, side-loading, and jailbreaking can weaken the security measures implemented by the device manufacturer and operating system and make it easier for attackers to exploit vulnerabilities, install malware, or gain unauthorized access to sensitive corporate information. By enabling access to unverified app stores or installing apps from unofficial sources, there is an increased risk of downloading malicious or compromised applications. Side-loading is generally associated with Android devices utilizing APK, Android Application Package, files. While applications can also be side-loaded on Apple devices, the practice directly violates Apple's terms and conditions. Page 13, Jailbroken Devices, https://www.apple.com/legal//iOS17_iPadOS17 PDF #. Voiding a device's licensing terms eliminates official support from the manufacturer, meaning the device may no longer receive security patches, bug fixes, or updates, leaving it vulnerable to new threats and exploits. Right to repair laws and the European Union's Digital Markets Act are challenging many of the software, licensing, and hardware protections that limit the ability to repair or reprogram devices. Organizations operating in regulated industries such as healthcare or finance should implement strict policies prohibiting rooting, side-loading, and jailbreaking due to the increased risk of data breaches and compliance violations. Mobile device management, MDM, platforms can detect and restrict rooting, jailbreaking, and side-loading. Regular employee education and awareness programs are also crucial to ensure employees understand the risks associated with these actions and adhere to the organization's mobile security policies. Mobile devices are often susceptible to the same types of vulnerabilities impacting desktop computers, such as insecure Wi-Fi connections, phishing attacks, and unpatched software vulnerabilities. Given their portable nature, mobile devices are also more likely to be lost or stolen, potentially exposing any unencrypted data stored on the device. Rate your confidence.
Topic 8b.
Application and cloud vulnerabilities. Exam objectives covered. 2.3 explain various types of vulnerabilities. Web and cloud-based applications introduce unique vulnerability concerns stemming from various sources, such as misconfigurations, insecure coding practices, and the use of third-party components with known vulnerabilities. Attackers can exploit these weaknesses to gain unauthorized access to sensitive data, disrupt services, or even compromise entire systems. In a cloud environment, shared responsibility models and multi-tenant architectures add complexity to vulnerability management. To address these concerns, developers and security professionals must employ secure coding practices, perform regular vulnerability assessments, and implement robust access controls. It is also essential to keep third-party components up to date and follow cloud provider-specific security recommendations. By understanding and proactively managing these vulnerabilities, organizations can ensure the security and reliability of their web and cloud-based applications, safeguarding valuable data and resources from potential cyberattacks.
Every organization presents an attack surface, and that's a fancy way of saying that it can have vulnerabilities in it based on its IT presence. To tell us more about the various types of vulnerabilities, we have Gareth Marchant. How you doing, Gareth?
Hey, great to be here, James. Good to see you.
Good to have you here, man. Gareth is owner of Lighthouse. Tell us more about Lighthouse, and let's start talking about vulnerabilities.
You bet. Lighthouse is a company I started about 5 years ago to help people develop their cybersecurity programs, train the workforce. Lots of cybersecurity things. I started the business after working in IT for about 25 years, um, and so here we are. But vulnerabilities is something that gets a lot of discussion. For obvious reasons. Folks want to understand, what weaknesses do I have? What issues exist in my environment that someone might take advantage of? And unfortunately, it's not an easy answer and it's not an easy thing to manage because, frankly, there are just so many of them.
That's right. I like how you talked about environment because there's so many elements of that environment, whether it
Yeah.
be applications or hardware or things in the cloud, virtualization, all these areas. Let's start
Yeah.
with applications. I have several friends of mine who are CIOs often will say, James, it's all in the applications. What
Yeah.
does that mean?
Yeah, the application is kind of like it's like the front cover of the book, it's what you see, it's what folks interact with, is what draws them in or what have you. But underneath there's so much that goes into creating that. There's so many layers to an application. Applications run on top of so many other parts of the IT infrastructure. So on the surface is a simple user interface with pointy clicky buttons and things like this. Under the behind the scenes, there's databases, there's different application servers, there's data interfaces, there's programming languages, platforms, all of these things. And every single part of those, including the user of the application, all have vulnerabilities that need to be identified and addressed.
So it's interesting you bring up that word application. So we're not just talking about the applications that run on your phone or that run on your desktop. You're talking about things that run on the server side, and they can run
Yeah,
into various types of issues like buffer overflows and
yeah,
injection attacks, right?
yeah. You're right. That's it. When we say application, it's so broad. It's
Mm.
everything from a web page, website, to an application on a tablet or a phone or a desktop computer, which might be running Windows or it might be running Mac or Linux or what have you. And so the very nature of that, I mean, it's a whole career path, right? Learning how to develop applications is hard.
Sure.
But it turns out that attackers, they're pretty good at application development too. They know about software languages and things. And so understanding how it works allows it to be manipulated to make it work in ways that developer didn't anticipate. And so you see things like SQL injection, cross-site scripting, and other types of attacks like this that are covered on the exam that describe how little snippets of code are sort of provided to the application in ways it wouldn't expect, and it changes the way that it works, and it can sometimes expose data or provide unauthorized access.
There are other types of issues. For example, with hardware, we have firmware that needs to be updated,
Yeah.
things like that. Yet sometimes you can't update the hardware, right?
It's true, especially with some of the consumer grade stuff. These things, what do we want when we buy this stuff? We want it to be inexpensive. And so in order to keep these things inexpensive, a lot of times they're kind of cranked out quickly. And then if there are issues with it, the answer is always, well, buy the new one. But if you think about it, even, at home, how many, if you think about, for example, the router that you use, to provide Wi-Fi, gain access to the internet, when did you buy that? When was the last time that thing was updated? Because I guarantee you there's vulnerabilities in it, but it's not always apparent. Something that have a vulnerability in it doesn't mean it stops working or starts blinking red or anything like this. It's just this quiet issue that sits there that's no big deal until it is.
And on the more industrial side, we have a lot of devices out there. I mean,
Yeah,
big devices, windmills,
yeah,
electricity generation, things like
yeah,
that. Those are governed by computers as well. And we have problems updating those as well,
yeah.
right?
Yeah, that's it. It really tells a story of how the software is everywhere,
Yeah.
from manufacturing plants, to the phones we hold in our hands and everything in between. It's all driven by software. Sometimes it's a small scale thing. It may just be a personal printer, uh, uh, but then it could be something bigger, like a control system that's used to say, regulate the pressure in a container that holds, some sort of, toxic waste. And so when those software applications are exploited, when they have issues, it literally results in death or natural disasters and things. So, I mean, the stakes couldn't really be much higher, right?
No, indeed. No, indeed. And it can even start when someone jailbreaks their phone, just playing with it, having fun with it. But then that introduces an unknown element into the organization. And
Yeah.
then you have another vulnerability happening, right?
Yeah, yeah, exactly. That's right. It's fun to do these things, but if you do that with like a work phone,
Yeah.
the problem is if that phone comes into contact with something that's malicious, because it's had the, sort of the security mechanisms bypassed, that one little phone can sometimes be the pathway an attacker takes in order to get into the bigger enterprise and all of the data and the systems that are there. So it seems like a small change. A lot of folks think, well, I'm just the little guy on the totem pole. I got nothing that anyone's going to want to come after me for. And it turns
Uh,
out that they're exactly the people that are being targeted.
Gareth, thanks so much for talking to us about vulnerabilities in the attack surface today. Appreciate it,
It's a
man.
pleasure, James. Thanks for having me.
Application vulnerabilities. Race condition and talk to. Application race condition vulnerabilities refer to software flaws associated with the timing or order of events within a software program, which can be manipulated, causing undesirable or unpredictable outcomes. A race condition describes when two or more operations must execute in the correct order. When software logic does not check or enforce the expected order of events, security issues such as data corruption, unauthorized access, or similar security breaches may occur. Race conditions manifest in a wide variety of ways, such as time of check to time of use, talk to vulnerabilities, where a system state changes between the check, verification, stage, and the use, execution, stage. Imagine a scenario where a multi-threaded banking application used one program thread to check an account balance and another thread to withdraw money. If an attacker manipulates the sequence of execution in this example, they could potentially overdraw the account. These vulnerabilities underscore the importance of atomic operations where checking and execution are done as a single, indivisible operation, mitigating the likelihood of exploitation. Two significant examples of race conditions include the dirty COW vulnerability, CV 2016-5195, which is a race condition vulnerability in the Linux kernel, allowing a local user to gain privileged access, and the Microsoft Windows Elevation of Privilege vulnerability, CV 2020-0796, which is a race condition vulnerability associated with the Microsoft Server Message Block 3.1.1 SMBv3 protocol, allowing an attacker to execute arbitrary code on a target SMB server or client. Race conditions are often mitigated by developers through the use of locks, semaphores, and monitors in multi-threaded applications. Memory injection. Memory injection vulnerabilities refer to a type of security flaw where an attacker can inject malicious code into a running application's process memory. An attacker often designs the injected code to alter an application's behavior to provide unauthorized access or control over the system. Injection vulnerabilities are significant because they often lead to severe security breaches. Attackers often use memory injection vulnerabilities to inject code that installs malware, exfiltrates sensitive data, or creates a backdoor for future access. Injected code generally runs with the same level of privileges as the compromised application, which can lead to a full system compromise if the exploited application has high-level permissions. Common memory injection attacks include buffer overflow attacks, format string vulnerabilities, and code injection attacks. These types of attacks are typically mitigated with secure coding practices such as input and output validation, encoding, typecasting, access controls, static and dynamic application testing, and several other techniques. Buffer overflow. A buffer is an area of memory that the application reserves to store expected data. To exploit a buffer overflow vulnerability, the attacker passes data that deliberately overfills the buffer. One of the most common vulnerabilities is a stack overflow. The stack is an area of memory used by a program subroutine. It includes a return address, which is the location of the program that called the subroutine. An attacker could use a buffer overflow to change the return address, allowing the attacker to run arbitrary code on the system. Buffer overflow attacks are mitigated on modern hardware and operating systems via address space layout randomization, ASLR, and data execution prevention, DEP, controls utilizing type-safe programming languages and incorporating secure coding practices.
Description.
Normal execution from top to bottom is sub stack, return address, main.
Main stack.
An arrow from main to sub is labeled arguments. Another arrow moves from return address to main. Exploit execution from top to bottom is sub, NOP, shellcode, NOP, return address, main stack. An arrow from main to sub is labeled as a danger symbol. Another arrow moves from return address to NOP in row 2. The third arrow moves from NOP in row 2 to shellcode. When executed normally, a function will return control to the calling function. If the code is vulnerable, an attacker can pass malicious data to the function, overflow the stack, and run arbitrary code to gain a shell on the target system. Malicious update. A malicious update refers to an update that appears legitimate but contains harmful code, often used by cybercriminals to distribute malware or execute a cyber attack. The update may claim to fix software bugs or offer new features, but is instead designed to compromise a system. The significance of such attacks lies in their deceptive nature. Users trust and frequently accept software updates, making malicious updates a highly effective infiltration strategy. Malicious updates can be difficult to protect against, but secure software supply chain management, digital signature verification, and other software security practices help mitigate these risks. In 2017, the legitimate software CCleaner was compromised when an unauthorized update was released containing a malicious payload. This affected millions of users who downloaded the update, believing it was a standard upgrade to improve their system's performance. https://ars-technica.com/information-technology/2017/09/backdoor-malvery-planted-in-dash-to-CCleaner. Another notable case is the 2020 SolarWinds attack, where attackers used an update to the SolarWinds Orion platform to distribute a malicious backdoor to numerous government and corporate networks, leading to significant data breaches. Evaluation scope. Evaluation target or scope refers to the product, system, or service being analyzed for potential security vulnerabilities. This could be a software application, a network, a security service, or even an entire IT infrastructure. The target is the focus of a specific evaluation process, where it is subjected to rigorous testing and analysis to identify any possible weaknesses or vulnerabilities in its design, implementation, or operation. For application vulnerabilities, the target would refer to a specific software application. Security analysts assess application code, logic, data handling, authentication mechanisms, and many other aspects relevant to its security. Identified vulnerabilities often range from common ones, such as injection flaws, broken authentication, and sensitive data exposure, to more obscure ones related to the application's unique features or purpose. The primary goal of the evaluation is to mitigate risk, improve the application's security posture, and ensure compliance with relevant security standards or regulations. Scope practice.
Description.
Security testing. Conducting vulnerability assessments and penetration testing to identify potential weaknesses, vulnerabilities, or misconfigurations. Documentation review. Reviewing documentation, such as design specifications, architecture diagrams, security policies, and procedures, to ensure the system is implemented according to secure design principles and compliance requirements. Source code analysis. Analyzing source code to identify potential security vulnerabilities or coding errors to uncover issues related to input validation, secure coding practices, and coding standards. Configuration assessment. Evaluating configuration settings to ensure they align with security best practices and industry standards, such as assessing access controls, encryption settings, authentication mechanisms, and other security-related configurations. Cryptographic analysis. Assessing cryptographic mechanisms, including encryption algorithms, key management, and secure key storage, to ensure the proper implementation and use of cryptographic schemes according to industry standards and guidelines. Compliance verification. Verifying compliance with standards specified by relevant regulations, frameworks, or security certifications. Security architecture review. Evaluating security architecture and design to identify potential weaknesses or gaps in security controls, such as insufficient segregation of duties, lack of audit trails, or inadequate access controls. Penetration tester versus attacker. From the perspective of a penetration tester or an attacker, the scope defines the boundaries of their objectives. For a penetration tester, the scope is the specific system, application, network, or environment they are authorized to evaluate for exploitability. Understanding the scope allows a penetration tester to plan their testing strategy, select appropriate tools and techniques, and focus their efforts where they will be most effective. Penetration testers aim to uncover as many vulnerabilities as possible within the scope, report their findings, and recommend remediation strategies to improve the system's security posture. For an attacker, the scope describes their intended target. The attacker aims to identify and exploit vulnerabilities within the target to achieve their objectives, which could range from unauthorized access and data theft to service disruption or even system takeover. An attacker's understanding of the target can influence their choice of attack vectors and the sophistication of their tactics. In both cases, a thorough understanding of the target, its architecture, components, interconnections, security controls, potential vulnerabilities, and value of its data or services helps to focus time and effort. Rate your confidence. Web application attacks. Web application attacks specifically target applications accessible over the internet, exploiting vulnerabilities in these applications to gain unauthorized access, steal sensitive data, disrupt services, or perform other malicious activities. The defining characteristics of web application attacks often involve the exploitation of poor input validation, leading to attacks like SQL injection or cross-site scripting, misconfigured security settings, and outdated software with known vulnerabilities. Web application attacks are similar to other types of application attacks in that they involve exploiting vulnerabilities in software to achieve malicious ends. However, they also have distinct differences. Unlike attacks on desktop applications or embedded systems, web application attacks must navigate the client-server model, often requiring the attacker to bypass network and application-level security controls. Also, web application vulnerabilities can often be exploited remotely by any attacker on the internet, making them a popular target for cybercriminals. HTTP is stateless, meaning each request is independent, and the server does not retain information about the client state. Web applications must manage sessions and maintain state-using mechanisms such as cookies or session IDs. Improper session management, such as predictable session IDs, session fixation, or session hijacking, are associated with many types of web application attacks, such as cross-site request forgery, CSRF, and cross-site scripting, XSS. These attacks exploit the web's inherent trust in requests or scripts that appear to come from valid users or trusted sites. CSRF is discussed in more depth in Lesson 13. Cross-site scripting, XSS. Web applications depend on scripting, and most websites these days are web applications rather than static web pages. If the user attempts to disable scripting, very few sites will be left available. A cross-site scripting, XSS, attack exploits the fact that the browser is likely to trust scripts that appear to come from a site the user has chosen to visit. XSS inserts a malicious script that appears to be part of the trusted site. A non-persistent type of XSS attack would proceed as follows. The attacker identifies an input validation vulnerability in the trusted site. The attacker crafts a URL to perform a code injection against the trusted site. This could be coded in a link from the attacker's site to the trusted site or a link in an email message. When the user clicks the link, the trusted site returns a page containing the malicious code injected by the attacker. As the browser is likely to be configured to allow the site to run scripts, the malicious code will execute. The malicious code could be used to deface the trusted site, by adding any sort of arbitrary HTML code, steal data from a user's cookies, try to intercept information entered into a form, perform a request forgery attack, or try to install malware. The crucial point is that the malicious code runs in the client's browser with the same permission level as the trusted site. An attack, where the malicious input comes from a crafted link, is a reflected or non-persistent XSS attack. A stored/persistent XSS attack aims to insert code into a backend database or content management system used by the trusted site. For example, the attacker may submit a post to a bulletin board with a malicious script embedded in the message. When other users view the message, the malicious script is executed. For example, with no input sanitization, a threat actor could type the following into a new post text field. Check out this amazing aref equals https://trusted foo website /a script src equals https://bad site foo/hook js/script. Users viewing the post will have the malicious script hook JS execute in their browser. A third type of XSS attack exploits vulnerabilities in client-side scripts. Such scripts often use the document object model, DOM, to modify the content and layout of a web page. For example, the document write method enables a page to take some user input and modify the page accordingly. An exploit against a client-side script could work as follows. The attacker identifies an input validation vulnerability in the trusted site. For example, a message board might take the user's name from an input text box and show it in a header. https://trusted foo/messages $user $James. The attacker crafts a URL to modify the parameters of a script that the server will return, such as the following. https://trusted foo/messages $user $James $3c script $20 src $3d $22 https $3 a $2f $2 fbad site foo $2 f hook js $22 $3 e $3c $2 f script $3e. The server returns a page with the legitimate DOM script embedded, but containing the parameter James script src equals https://bad site foo/hook js/script. The browser renders the page using the DOM script, adding the text James to the header but also executing the hook JS script at the same time. DOM-based cross-site scripting, XSS, occurs when a web application's client-side script manipulates the document object model, DOM, of a web page. Unlike other forms of XSS attacks that exploit server-side vulnerabilities, DOM-based XSS attacks target the client-side environment, allowing an attacker to inject malicious script code executed within the user's browser within the context of the targeted web page. SQL injection, SQL, where an overflow attack works against the way a process performs memory management. An injection attack exploits some unsecure way in which the application processes requests and queries. For example, an application might allow a user to view their profile with a database query that should return the single record for that one user's profile. An application vulnerable to an injection attack might allow a threat actor to return the records for all users, or to change fields in the record when they are only supposed to be able to read them. A web application is likely to use structured query language, SQL, to read and write information from a database. The main database operations are performed by SQL statements for selecting data, select, inserting data, insert, deleting data, delete, and updating data, update. In a SQL injection attack, the threat actor modifies one or more of these four basic functions by adding code to some input accepted by the app, causing it to execute the attacker's own set of SQL queries or parameters. If successful, this could allow the attacker to extract or insert information into the database or execute arbitrary code on the remote system using the same privileges as the database application, OWASP, org/www-community/attacks/SQL_injection. For example, consider a web form that is supposed to take a name as input. If the user enters Bob, the application runs the following query. Select asterisk from TBL_user where username equals Bob. If a threat actor enters the string or 1=1 hashtag and this input is not sanitized, the following malicious query will be executed. Select asterisk from TBL_user where username equals or 1=1 hashtag. The logical statement 1 is equal to 1 is always true, and the hashtag character turns the rest of the statement into a comment, making it more likely that the web application will parse this modified version and dump a list of all users. Rate your cloud-based application attacks. Cloud-based application attacks target applications hosted on cloud platforms and exploit potential vulnerabilities within these applications or the cloud infrastructure they run on to carry out malicious activities. Cloud-based application attacks generally involve the exploitation of misconfigurations in the cloud environment, weak authentication mechanisms, insufficient network segmentation, or poorly implemented access controls. Compared to traditional application attacks, cloud-based attacks have some unique characteristics. In a cloud environment, the shared responsibility model can lead to confusion about who is responsible for what, potentially leaving security gaps that attackers can exploit. The highly accessible and scalable nature of the cloud can make cloud-based applications attractive targets for attackers. For example, an attacker may exploit a vulnerability in a cloud-based application resulting in access to other resources within the same cloud environment, providing access to infrastructure in ways typically impossible with traditional application attacks. Some attack types are largely specific to the cloud, such as side-channel attacks, where an attacker with an instance running on the same physical server as the victim attempts to extract information from the victim's instance via shared resources. Attackers can exploit misconfigurations and weak security controls in cloud environments to gain unauthorized access to sensitive data in improperly secured cloud storage buckets. Cloud services can also be used for cryptojacking, where an attacker uses the cloud's processing power to mine cryptocurrency without the user's consent, leading to, vastly, increased costs for the cloud user and degraded performance of their provisioned resources. The shared responsibility model is covered in Module 3, Security Architecture, Responsibility Matrix. Cloud as an attack platform. Attackers can also use cloud platforms for phishing and malware distribution. They can easily set up fraudulent websites that mimic legitimate ones on cloud services and use these sites to trick users into revealing sensitive information. In addition, they can exploit cloud storage services to host malicious files and then distribute these files via phishing emails or other means. Cloud Access Security Brokers. A Cloud Access Security Broker, CSB, is enterprise management software designed to mediate access to cloud services by users across all types of devices. CSP vendors include Symantec, Broadcom.com/products/cyber-security/information-protection/cloud-application-security-clouds-OC, Skyhigh Security, skyhighsecurity.com, ForcePoint, CASCs provide visibility into how clients and other network nodes are using cloud services. Some of the functions of a CSP are the following. Enable single sign-on authentication and enforce access controls and authorizations from the enterprise networked to the cloud provider. Scan for malware and rogue or non-compliant device access. Monitor and audit user and resource activity. Mitigate data exfiltration by preventing access to unauthorized cloud services from managed devices. In general, CASPs are implemented in one of three ways. Forward proxy is a security appliance or host positioned at the client network edge that forwards user traffic to the cloud network if the contents of that traffic comply with the policy. This requires configuration of users' devices or installation of an agent. In this mode, the proxy can inspect all traffic in real time, even if that traffic is not bound for sanctioned cloud applications. The problem with this mode is that users may be able to evade the proxy and connect directly. Proxies are also associated with poor performance, as without a load balancing solution, they become a bottleneck and potentially a single point of failure. Reverse proxy is positioned at the cloud network edge and directs traffic to cloud services if the contents of that traffic comply with the policy. This does not require configuration of the user's devices. This approach is only possible if the cloud application has proxy support. Application Programming Interface, API, brokers connections between the cloud service and the cloud consumer rather than placing a CSP appliance or host inline with cloud consumers and the cloud services. For example, if a user account has been disabled or an authorization has been revoked on the local network, the API-based CSP would communicate this to the cloud service and use its API to disable access thereto. This depends on the API supporting the range of functions that the CSP and access and authorization policies demand. CSP solutions are quite likely to use both proxy and API modes for different security management purposes. Rate
Supply chain.
Software supply chain vulnerabilities refer to the potential risks and weaknesses introduced into software products during their development, distribution, and maintenance lifecycle. This supply chain describes many stages, from initial coding to end-user deployment, and includes various service providers, hardware providers, and software providers. Service providers. Service providers, such as cloud services or third-party development agencies, play a role in the software supply chain by offering development, testing, and deployment platforms or directly contributing to the software's codebase. Vulnerabilities can be introduced if these services have inadequate security measures or if the communication between these services and the rest of the supply chain is not secured correctly. Hardware suppliers. Hardware suppliers play a crucial role in the software supply chain and can be potential sources of vulnerabilities. The hardware on which software runs or interacts forms the base of the technology stack. If this hardware layer is compromised, it can lead to severe security issues. This is particularly true for firmware or low-level software drivers interacting closely with the hardware. If a hardware supplier fails to apply robust security practices in their design and manufacturing processes, it can introduce vulnerabilities that compromise the entire system. For example, a hardware component could come with pre-installed firmware that contains a known vulnerability, or it might be susceptible to physical tampering that leads to a breach in security. Similarly, hardware devices often require specific drivers to function correctly. If these drivers are not updated regularly or are sourced from unreliable providers, they can introduce vulnerabilities into the software stack. Furthermore, hardware suppliers often provide the entire software stack running on the device for IoT and embedded systems, making them a significant factor in a system's overall security. Therefore, it's crucial for software supply chain security to ensure that hardware suppliers adhere to stringent security standards and that hardware components and associated low-level software are regularly updated and patched to address any potential vulnerabilities. Software providers. Software providers, including makers of libraries, frameworks, and other third-party components used in the software, are a common source of vulnerabilities. If third-party components have vulnerabilities or are outdated, they can expose the entire application to potential attacks. In all these relationships, trust is implicitly placed in each provider to maintain high security. If any link in this chain fails to meet these expectations, it can lead to software supply chain vulnerabilities. Software Bill of Materials. A Software Bill of Materials, SBOM, is a comprehensive inventory of all components in a software product. This includes the primary application code and all dependencies, such as libraries, frameworks, and other third-party components. The SVOM includes details like component names, versions, and information about the suppliers. An SBOM aims to provide transparency and visibility into the software supply chain, which can significantly help mitigate software supply chain issues. By detailing all components used in a software product, an SEOM enables developers, security teams, and end users to understand the functional components of their software. This visibility aids in identifying potential vulnerabilities in third-party components, allowing them to be patched or replaced before issues materialize. It also helps track software components' origin, ensuring they come from trusted sources. After a vulnerability disclosure or a security incident, an SBOM supports rapid response and remediation. Security teams can quickly determine whether their software is affected by a disclosed vulnerability in a particular component and take appropriate action. An SBOM is a critical tool for managing and securing the software supply chain because it contributes to a more proactive and informed approach to identifying and managing potential software supply chain issues. Dependency analysis and SBOM tools. The OWASP dependency check is a software composition analysis (SCA) tool that identifies project dependencies and checks if there are any known, publicly disclosed vulnerabilities associated with them. This tool is very useful for creating a software bill of materials (SBOM), although it's not its primary function. Dependency Check can generate a report detailing all the libraries and components used in a software project and their respective versions. This type of report serves as a baseline for creating an SEOM, as it lists all the components that the software depends upon. Furthermore, the report includes known vulnerabilities associated with these components, a valuable addition to an SBOM from a security perspective. Dependency Check is designed primarily to assist in detecting outdated or vulnerable components and does not provide all of the information typically included in an SEOM, such as licensing information or a complete list of all subcomponents. For a more comprehensive SEOM that includes additional information, other tools like OWASP Dependency Track use the output from Dependency Check or other dedicated SEOM tools that follow SPDX or OWASP CycloneDX standards. SPDX, Software Package Data Exchange, is an open standard for communicating software bill of material information, including component identification, licensing, and security references. CycloneDX is a lightweight specification designed to provide a more streamlined way to share and analyze SBOM data. Rate your vulnerability identification methods. Exam objectives covered. 4.3 explain various activities associated with vulnerability management. Vulnerability scanning is a fundamental task within a vulnerability management program and utilizes automated scanning processes to identify and evaluate potential issues. Vulnerability scans focus on networks, operating systems, applications, and other functional areas to detect known vulnerabilities, including insecure configurations, outdated software versions, or missing security patches. Regular scanning is required to maintain an accurate picture of an organization's security posture and to identify new vulnerabilities. Threat feeds play a vital role in enhancing the effectiveness of vulnerability management by providing real-time information about emerging threats and newly discovered vulnerabilities. Threat feeds aggregate data from various sources, including cybersecurity researchers, vendors, and global security communities, and are integrated into vulnerability scanning tools to improve their detection capabilities. By leveraging threat feeds, organizations can stay ahead of the threat landscape, enabling them to prioritize and address the most critical vulnerabilities before attackers can exploit them. Vulnerability scanning. Vulnerability management is a cornerstone of modern cybersecurity practices aimed at identifying, classifying, remediating, and mitigating vulnerabilities within a system or network. One crucial aspect of vulnerability management is vulnerability scanning, a systematic process of probing a system or network using specialized software tools to detect security weaknesses. Vulnerability scans are performed internally and externally to inventory vulnerabilities from different network viewpoints. Vulnerabilities identified during scanning are then classified and prioritized for remediation by security operations teams. Vulnerability scanning also supports application security, as it helps to locate and identify misconfigurations and missing patches in software. Advanced vulnerability scanning techniques focused on application security include specialized application scanners, pen testing frameworks, and static and dynamic code testing. Vulnerability scanning tools like OpenVS and Nessus are popular tools offering a broad range of features designed to analyze network equipment, operating systems, databases, patch compliance, configuration, and many other systems. While these tools are very effective, application security analysis warrants much more specialized approaches. Several specialized tools exist to more deeply analyze how applications are designed to operate and can locate vulnerabilities not typically identified using generalized scanning approaches. Network Vulnerability Scanner. A network vulnerability scanner, such as Tenable Nessus, tenable.com/products/nessus, or OpenVS, openvast.org, is designed to test network hosts, including client PCs, mobile devices, servers, routers, and switches. It examines an organization's on-premises systems, applications, and devices, and compares the scan results to configuration templates and lists of known vulnerabilities. Typical results from a vulnerability assessment will identify missing patches, deviations from baseline configuration templates, and other related vulnerabilities. Description. The first section is a donut chart. The whole chart represents high. The second section, titled Task by Status, Total 1, shows a donut chart. The whole chart represents done. The third section, titled CVs by Creation Time, Total 85015, shows a line graph with 2 lines representing CVs per year and total CVs. The fourth section, titled Host Topology, shows a node labeled 10.1.0.104 at the center, connected to 4 other nodes labeled 10.1.0.1, 10.1.0.2, 10.1.0.102, and 10.1.0.103. The fifth section, titled NVDs by Severity Class, shows a donut chart with 4 sections. High, 26,381. Medium, 21621. Low, 2022. And log, 2664. GreenOwn OpenVS Vulnerability Scanner with Security Assistant Web Application Interface, as installed on Kali Linux. Screenshot used with permission from GreenOwn Networks, http://www.openvast.org. Scanners depend upon a database of known software and configuration vulnerabilities. The tool compiles a report about each vulnerability in its database that was found to be present on each host. Each identified vulnerability is categorized and assigned an impact warning. Most tools also suggest remediation techniques. This information is highly sensitive, so use of these tools and the distribution of the reports produced should be restricted to authorized hosts and user accounts. Network vulnerability scanners are configured with information about known vulnerabilities and configuration weaknesses for typical network hosts. These scanners will be able to test common operating systems, desktop applications, and some server applications. This is useful for general-purpose scanning, but some types of applications might need more rigorous analysis. Credentialed and non-credentialed scans. A non-credentialed scan is one that proceeds by directing test packets at a host without being logged on to the OS or application. The view is the one the host exposes to an unprivileged user on the network. The test routines may be able to include things such as using default passwords for service accounts and device management interfaces, but they are not given privileged access. While you may discover more weaknesses with a credentialed scan, you will sometimes want to narrow your focus to that of an attacker who doesn't have specific high-level permissions or total administrative access. Non-credentialed scanning is the most appropriate technique for external assessment of the network perimeter or when performing web application scanning. A credentialed scan is giving a user account with login rights to various hosts, plus whatever other permissions are appropriate for the testing routines. This sort of test allows much more in-depth analysis, especially in detecting when applications or security settings may be misconfigured. It shows what an insider attack, or an attack with a compromised user account, may be able to achieve. A credentialed scan is a more intrusive type of scan than non-credentialed scanning.
Description.
The menu bar on the top has options: scan management, asset management, SEC info management, configuration, extras, administration, and help. The new credential window has boxes to enter the following details. Name, classroom domain.
Login, Classroom/Administrator.
Comment, optional blank. Auto-generate credential with a non-selected radio button. The radio button for password is selected, and the password is entered in the box next to it. Key pair with a non-selected radio button. Private key followed by a browse button. Passphrase, blank. A create credential button is at the bottom right. Configuring credentials for use in target, scope, definitions in Greenone OpenVS as installed on Kali Linux. Screenshot used with permission from Greenone Networks, http://www.openvas.org. Application and web application scanners. Similarly, application vulnerability scanning describes a specialized vulnerability scanning method for identifying software application weaknesses. This includes static analysis, reviewing application code without executing it, and dynamic analysis, testing running applications, which can identify issues like unvalidated inputs, broken access controls, and SQL injection vulnerabilities. Application vulnerability scanning is typically handled separately from general vulnerability scanning due to the unique nature of software applications and the specific types of vulnerabilities they introduce. General vulnerability scanning is designed to detect system-wide or network-wide weaknesses, such as out-of-date software or misconfigured firewalls. In contrast, application vulnerability scanning evaluates the coding and behavior of individual software applications. It looks for issues like cross-site scripting, XSS, SQL injection, and insecure direct object references unique to software applications. These application-specific vulnerabilities require specialized tools and techniques to identify and mitigate and are generally different from the scanning tools used in general vulnerability scanning. Applications frequently have their own release and update cycles, separate from the rest of the environment, necessitating a more targeted vulnerability management process. Package monitoring. Another important capability in application vulnerability assessment practices includes package monitoring. Package monitoring is associated with vulnerability identification because it tracks and assesses the security of third-party software packages, libraries, and dependencies used within an organization to ensure that they are up to date and free from known vulnerabilities that malicious actors could exploit. Package monitoring is associated with the management of software bill of materials, SBOM, and software supply chain risk management practices. In an enterprise setting, package monitoring is typically achieved through automated tools and governance policies. Automated software composition analysis, SCA, tools track and monitor the software packages, libraries, and dependencies used in an organization's codebase. These tools can automatically identify outdated packages or packages with known vulnerabilities and suggest updates or replacements. They work by continuously comparing the organization's software inventory against various databases of known vulnerabilities, such as the National Vulnerability Database, NVD, or vendor-specific advisories. In addition to these tools, organizations often implement governance policies around software usage. These policies may require regular audits of software packages, approval processes for adding new packages or libraries, and procedures for updating or patching software when vulnerabilities are identified.
In this demonstration, we're going to work with the Nessus Vulnerability Scanner. Nessus is a very powerful security tool that you can use to scan for security vulnerabilities on your network. Nessus is accessed via a web page on port 8834. I've installed Nessus on this machine, so I'm just connecting to localhost. For this demo, I'm running an evaluation copy of Nessus, but that's sufficient to show what it can do. Let's start by logging in. After I log in, we see the home page. Here, we can see the various scans that have already been created. There are many different features and options in Nessus, but for this demo, I'll stick to showing how to create and run a network scan. While I could create a custom scan profile, Nessus includes quite a few useful templates that can accomplish most of what I typically need. To create a scan, I'll start by selecting New Scan from the top right. Here, we can see some of the templates I mentioned. I'm going to run a basic network scan, so I'll select that template. This template scans a specified host or network range for known vulnerabilities. To set up the scan, I'll need to provide a name for it, as well as a network address that I'd like to scan. I'm going to name this Home Gateway Scan, since I'll be scanning the computers at my house with it. My gateway is located at 10.0.0.1, so that's what I'll supply as the target. There are many other options that I could configure, including port discovery and authenticated scanning, but I just want to do a simple scan today. Since everything I need is configured, I'll click Save. Now that I've returned to the home page, I can see that the new scan has been created but isn't running yet. I can click Launch to start it. The scan's title changes to bold, and a spinning green icon appears to show that the scan is active. I can watch the scan live by clicking on it. This screen shows information about the different hosts that are discovered and the vulnerabilities that are found. Nessus also keeps a historical log of all the times a scan has been run so that I can compare how vulnerabilities have improved on my network over time. This scan is going to take a while, so I'll pause the demo until it's finished. Now that the scan has finished, we can see that my gateway has quite a few vulnerabilities. Luckily, most of them are labeled as informational. This means that the tool found information that could be useful for a security administrator to know about a host, but that the information doesn't immediately indicate a problem. An example of the type of data that would be labeled as informational is a list of open network ports. Network ports have to be open on some machines for them to function properly, but opening unexpected ports can cause problems. More serious vulnerabilities are color-coded from green to red. Low-severity vulnerabilities aren't as interesting as high or critical vulnerabilities, so I'll take a look at one of the worst issues Nessus found. When I select a vulnerability, it shows me information about the issue. In many cases, software creators patch high and critical vulnerabilities, and a relevant CVE entry is listed. Nessus provides a description and a suggested solution for many issues, as well as relevant information related to the vulnerability. And that's it for this demo. We discussed how to conduct a vulnerability scan with Nessus. We looked at what Nessus is and what it does, and we ran a vulnerability scan on my home network and explored the results.
Threat feeds. Another important element of vulnerability management is the use of threat feeds. These are real-time, continuously updated sources of information about potential threats and vulnerabilities, often gathered from multiple sources. By integrating threat feeds into their vulnerability management practices, organizations can stay aware of the latest risks and respond more swiftly. Threat feeds are pivotal in vulnerability scanning by providing real-time, continuous data about the latest vulnerabilities, exploits, and threat actors. These feeds serve as a valuable resource for enhancing the organization's threat intelligence and enabling quicker identification and remediation of potential vulnerabilities. They integrate data from various sources, including security vendors, cybersecurity organizations, and open-source intelligence, to comprehensively view the threat landscape. Common threat feed platforms include Alien Vault's Open Threat Exchange, OTX, IBM's X-Force Exchange, and Recorded Future. These platforms gather, analyze, and distribute information about new and emerging threats, providing actionable intelligence that can be incorporated into an organization's vulnerability management practices and sometimes directly into security infrastructure tools to provide up-to-the-minute protections. Threat feeds significantly improve vulnerability identification by providing timely information and context about new threats that traditional vulnerability scanning does not provide. Threat feeds provide information that helps organizations focus their remediation efforts on the most relevant and potentially damaging vulnerabilities first. This proactive approach can significantly reduce the time between discovering a vulnerability and its remediation, thus minimizing the organization's exposure to potential attacks. Third-party threat feeds. Open source and proprietary threat feeds provide valuable real-time information on the latest cyber threats and vulnerabilities. Both feed types aggregate data from various sources and can be integrated into an organization's security infrastructure, contributing to a proactive cybersecurity strategy. The choice between open source and proprietary threat feeds often comes down to a few important attributes. Open source feeds, such as those provided by the Cyber Threat Alliance or the MISP threat sharing platform, are typically free and accessible to all, making them a cost-effective solution for smaller organizations or those with limited budgets. However, they may lack the depth, breadth, or sophistication of analysis found in proprietary feeds. Proprietary threat feeds often provide more comprehensive information and advanced analytic insights. However, these feeds come at a cost, and the return on investment will depend on an organization's specific needs, risk profile, and resources. Some organizations may use a combination of both open source and proprietary feeds to achieve a balance of cost and coverage. Description. The text on the top left reads, "Research, collaborate, and act on threat intelligence." Below the text is a search bar followed by the trending links on the top right. The dashboard below shows 5 sections: IBM Advanced Threat Protection Feed, Early Warning Feed, Iris Threat Intelligence, recent IBM X-Force advisories, and threat activity. The first 2 sections are followed by a button to start a 30-day trial. IBM X-Force Exchange Threat Intelligence Portal. Image copyright 2019 IBM Security Exchange, X-Force, ibmcloud.com. The outputs from the primary research undertaken by threat data feed providers and academics can take 3 main forms. Behavioral threat research is narrative commentary describing examples of attacks and TTPs gathered through primary research sources. Reputational threat intelligence is lists of IP addresses and domains associated with malicious behavior, plus signatures of known file-based malware. Threat data is computer data that can correlate events observed on a customer's own networks and logs with known TTP and threat actor indicators. Threat data can be packaged as feeds that integrate with a security information and event management (SIEM) platform. These feeds are usually described as cyber threat intelligence (CTI) data. The data on its own is not a complete security solution. To produce actionable intelligence, the threat data must be correlated with observed data from customer networks. This type of analysis is often powered by artificial intelligence (AI) features of the SIEM. Threat intelligence platforms and feeds are often supplied on a closed/proprietary basis. A proprietary feed is where threat research and CTI data is available as a paid subscription to a commercial threat intelligence platform. The security solution provider will also make the most valuable research available early to platform subscribers in the form of blogs, white papers, and webinars. Some examples of such platforms include the following: IBM X-Force Exchange, X-Force, ibmcloud.com, Mandiant's FireEye Cloud. Information sharing organizations. Threat feed information sharing organizations are collaborative groups that exchange data about emerging cybersecurity threats and vulnerabilities. These organizations collect, analyze, and disseminate threat intelligence from various sources, including their members, security researchers, and public sources. Members of these organizations, often composed of businesses, government entities, and academic institutions, can benefit from the shared intelligence by gaining insights into the latest threats they might not have access to individually. They can use this information to fortify their systems and respond swiftly to emerging threats. Examples of such organizations include the Cyber Threat Alliance and the Information Sharing and Analysis Centers, ISACs, which span various industries. These organizations are crucial in enhancing collective cybersecurity resilience and promoting a collaborative approach to tackling cyber threats. Open Source Intelligence. Open Source Intelligence, OSINT, describes collecting and analyzing publicly available information and using it to support decision-making. In cybersecurity operations, OSINT is used to identify vulnerabilities and threat information by gathering data from many sources such as blogs, forums, social media platforms, and even the dark web. This can include information about new types of malware, attack strategies used by cybercriminals, and recently discovered software vulnerabilities. Security researchers can use OSINT tools to automatically collect and analyze this information, identifying potential threats or vulnerabilities that could impact their organization. Some common OSINT tools include Shodan for investigating internet-connected devices, Multigo for visualizing complex networks of information, Reconning for web-based reconnaissance activities, and the Harvester for gathering emails, subdomains, hosts, and employee names from different public sources. The OSINT framework is a useful resource designed to help locate and organize tools used. Intelligence. https://github.com/lockefail/osint-framework. OSINT can provide valuable context to aid in assessing risk levels associated with a specific vulnerability. For example, newly discovered vulnerabilities that are being actively exploited in the wild or discussed in hacking forums will need to be prioritized for remediation. In this way, OSINT helps identify vulnerabilities and plays a critical role in vulnerability management and threat assessment. Deep and dark web. Threat research is a counterintelligence gathering effort in which security companies and researchers attempt to discover the tactics, techniques, and procedures, TTPs, of modern cyber adversaries. There are many companies and academic institutions engaged in primary cybersecurity research. Security solution providers with firewall and anti-malware platforms derive a lot of data from their own customers' networks. As they assist customers with cybersecurity operations, they are able to analyze and publicize TTPs and their indicators. These organizations also operate honey-nets to try to observe how hackers interact with vulnerable systems. The deep web and dark web are also sources of threat intelligence. The deep web is any part of the World Wide Web that is not indexed by a search engine. This includes pages that require registration, pages that block search indexing, unlinked pages, pages using non-standard DNS, and content encoded in a non-standard manner. Within the deep web are areas that are deliberately concealed from regular browser access. Darknet is a network established as an overlay to internet infrastructure by software such as the Onion Router, TUR, Freenet, or I2P that acts to anonymize usage and prevent a third party from knowing about the existence of the network or analyzing any activity taking place over the network. Onion routing, for instance, uses multiple layers of encryption and relays between nodes to achieve this anonymity. Dark web is sites, content, and services accessible only over a dark net. While there are dark web search engines, many sites are hidden from them. Access to a dark website via its URL is often only available via word-of-mouth bulletin boards.
Description.
A context menu overlapping the screen shows the options, new identity, new Tor circuit for the site, security settings, Tor network settings, and check for Tor browser update on the left and the Tor circuit for this site on the right. Using the TUR browser to view the Alphabi market, now closed by law enforcement. Screenshot used with permission from Security Onion. Investigating these dark websites and message boards is a valuable source of counterintelligence. The anonymity of dark web services has made it easy for investigators to infiltrate the forums and web stores that have been set up to exchange stolen data and hacking tools. As adversaries react to this, they're setting up new networks and ways of identifying law enforcement infiltration. Consequently, dark nets and the dark web represent a continually shifting landscape. Please note that participating in illegal activities on the dark web is strictly prohibited. To stay safe, it is important to exercise caution and follow legal and ethical guidelines when exploring the dark web. The dark web is generally associated with illicit activities and illegal content, but it also has legitimate purposes. Privacy and anonymity. The dark web provides a platform for enhanced privacy and anonymity. It allows users to communicate and browse the internet without revealing their identity or location, which can be valuable for whistleblowers, journalists, activists, or individuals living under repressive government regimes. Access to censored information. In countries with strict internet censorship, the dark web can be an avenue for accessing information that is otherwise blocked or restricted. It enables individuals to bypass censorship and access politically sensitive or controversial content. Research and information sharing. Some academic researchers or cybersecurity professionals may explore the dark web to gain insights into criminal activities and analyze emerging threats to improve cybersecurity operations. Other vulnerability assessment methods. Penetration testing. Penetration testing, or pen testing, is a more aggressive approach to vulnerability management. Ethical hackers attempt to breach an organization's security in this practice, exploiting vulnerabilities to demonstrate their potential impact. While automated vulnerability scans and threat feeds are essential components of a robust security program, they may sometimes fail to identify specific vulnerabilities that a penetration test can uncover. Penetration testing involves human ingenuity and creativity, which allows for discovering complex vulnerabilities that automated tools often miss. For example, vulnerabilities introduced by the application's design and implementation and not coding errors can often go unnoticed by automated scanners. Penetration testers can manipulate an application's functionality to perform actions in ways not intended by its developers, leading to exploitation. Certain types of authentication bypass vulnerabilities or chained vulnerabilities, where multiple minor issues can be combined to create a significant security flaw, are often beyond the detection capabilities of automated scanning tools. Penetration tests also excel at identifying vulnerabilities associated with improper configurations or weak security policies. While automated scanning methods provide critical vulnerability data, penetration testing provides a deeper and more comprehensive analysis of an organization's security posture. Unknown environment, previously known as black box testing, is when the consultant/attacker has no privileged information about the network and its security systems. This type of test requires the consultant/attacker to perform an extensive reconnaissance phase. These tests are useful for simulating the behavior of an external threat. Known environment, previously known as white box testing, is when the consultant/attacker has complete access to information about the network. These tests are useful for simulating the behavior of a privileged insider threat. Partially known environment, previously known as gray box testing, is when the consultant/attacker has some information. This type of test requires partial reconnaissance on the part of the consultant/attacker. Bug bounties. Bug bounty programs are another proactive strategy and describe when organizations incentivize discovering and reporting vulnerabilities by offering rewards to external security researchers or white hat hackers. Both penetration testing and bug bounty programs are proactive cybersecurity practices to identify and mitigate vulnerabilities in a system or application. They both involve exploiting vulnerabilities to understand their potential impact, with the difference lying primarily in who conducts the testing and how it's structured. Penetration testing is typically performed by a hired team of professional ethical hackers within a confined time frame, using a structured approach based on the organization's requirements. This approach allows for a focused, in-depth examination of specific systems or applications and provides a predictable cost and timeline. In contrast, bug bounty programs open the testing process to a global community of independent security researchers. Rewards for finding and reporting vulnerabilities incentivize these researchers. This approach can bring diverse skills and perspectives to the testing process, potentially uncovering more complex or obscure vulnerabilities. An organization may choose penetration testing for a more controlled, targeted assessment, especially when testing specific components or meeting certain compliance requirements. A bug bounty program might be preferred when seeking a more extensive range of testing, leveraging the collective skills of a global community. However, many organizations see the value in both and use a combination of pen testing and bug bounty programs to ensure comprehensive vulnerability management.
Description.
The HackerOne logo on the top left is followed by expand buttons for solutions, products, partners, company, hackers, and resources. The screen reads, One Platform. Preemptive security. Delivered. Outmatch cybercriminals with a legion of ethical hackers who work for you to continuously protect your attack surface. 2 buttons, Explore the Platform, selected, and Request a Demo are at the bottom of the text. A donut chart titled Top Weaknesses and an area graph titled Weakness Trends are present on the right. The HackerOne platform is designed to support security researchers and promote responsible disclosure of vulnerabilities. Screenshot used with permission from HackerOne. Responsible disclosure programs are established by organizations to encourage individuals to report security vulnerabilities in software or systems, allowing the organization to address and fix these vulnerabilities before they can be exploited maliciously. Responsible disclosure programs provide guidelines and procedures for reporting vulnerabilities and often offer rewards or recognition to individuals who responsibly disclose verified security issues. Auditing. Auditing is an essential part of vulnerability management. Where product audits focus on specific features, such as application code, systems/process audits interrogate the wider use and deployment of products, including supply chain, configuration, support, monitoring, and cybersecurity. Security audits assess an organization's security controls, policies, and procedures, often using standards like ISO 27001 or the NIST Cybersecurity Framework as benchmarks. These audits can identify technical vulnerabilities and operational weaknesses impacting an organization's security posture. Cybersecurity audits are comprehensive reviews designed to ensure an organization's security posture aligns with established standards and best practices. There are various types of cybersecurity audits, including compliance audits, which assess adherence to regulations like GDPR or HIPAA, risk-based audits, which identify potential threats and vulnerabilities in an organization's systems and processes, and technical audits, which delve into the specifics of the organization's IT infrastructure, examining areas like network security, access controls, and data protection measures. Penetration testing fits into cybersecurity audit practices as a critical component of a technical audit as it provides a practical assessment of the organization's defenses by simulating real-world attack scenarios. Rather than simply evaluating policies or configurations, penetration tests actively seek exploitable vulnerabilities, providing a clear picture of what an attacker might achieve. The findings from these tests are then used to improve the organization's security controls and mitigate identified risks. Penetration tests also play an important role in compliance audits, as many regulations require organizations to conduct regular penetration testing as part of their cybersecurity program. For instance, the Payment Card Industry Data Security Standard, PCI DSS, mandates annual and proactive penetration tests for organizations handling cardholder data. Vulnerability analysis and remediation. Exam objectives covered. 4.3 explain various activities associated with vulnerability management. Vulnerability analysis and remediation are critical stages in vulnerability management. Vulnerability analysis involves evaluating vulnerabilities for their potential impact and exploitability. This process might consider factors such as the ease of exploitation, the potential damage from a successful exploit, the value of the vulnerable asset, and the current threat landscape. Vulnerability analysis helps prioritize remediation efforts, ensuring the most critical vulnerabilities are addressed first. Remediation describes how vulnerabilities are addressed to mitigate their potential risk. Mitigation techniques generally include applying patches, changing configurations, updating software, or replacing vulnerable systems. When immediate remediation is impossible, compensating controls describe alternative plans to reduce the risk. Verification that remediation efforts have been successful is accomplished via several methods, including rescanning affected systems. Organizations can significantly improve their resilience against cyber attacks by carefully analyzing and remediating vulnerabilities. Common vulnerabilities and exposures. An automated scanner needs to be kept up to date with information about known vulnerabilities. This information is often described as a vulnerability feed, though the Nessus tool refers to these feeds as plugins and OpenVS refers to them as Network Vulnerability Tests, NVDs. Often, the vulnerability feed forms an important part of scan vendors' commercial models because the latest updates require a valid subscription. Checking feed status in the Greenbone Community Edition Vulnerability Manager. Screenshot. Greenbone Community Edition Greenbone net/n/community-edition. The National Vulnerability Database, NVD, is a repository maintained by the National Institute of Standards and Technology, NIST, that provides detailed information about known software vulnerabilities, including vulnerability descriptions, severity ratings, affected software versions, and mitigation measures. https://nvd. NIST.gov. Vulnerability feeds use common identifiers to facilitate sharing of intelligence data across different platforms. Many vulnerability scanners use the Security Content Automation Protocol, SCAP, to obtain feed or plugin updates, SCAP, NIST.gov. As well as providing a mechanism for distributing the feed, SCAP defines ways to compare the actual configuration of a system to a target secure baseline plus various systems of common identifiers. These identifiers supply a standard means for different products to refer to a vulnerability or platform consistently. Common Vulnerabilities and Exposures, CV, is a dictionary of vulnerabilities Application Software, CVE, MITRE.org. The elements that make up a vulnerabilities entry in the CVE include an identifier in the format CVYYYY-######, where YYYY is the year the vulnerability was discovered and ###### is at least 4 digits that indicate the order in which the vulnerability was discovered. A brief description of the vulnerability. A reference list of URLs that supply more information on the vulnerability. The date the vulnerability entry was created. The CVE dictionary provides the principal input for NIST's National Vulnerability Database, NVD. NIST.gov. The NVD supplements the CVE descriptions with additional analysis, a criticality metric calculated using the Common Vulnerability Scoring System, CVSS, plus fix information. The Forum of Incident Response and Security Teams maintains the CVSS, first org/CVSS. CVSS metrics generate a score from 0 to 10 based on the characteristics of the vulnerability, such as whether it can be triggered remotely or needs local access, whether user intervention is required, and so on. The scores are banded into descriptions as follows.
Score. Description.
0.1 plus.
Low.
False positives, false negatives, and log review. After completing a vulnerability scan, the tool generates a summary report of all discoveries. The report color codes vulnerabilities based on their criticality, with red typically denoting a weakness that requires immediate attention. Vulnerabilities can be reviewed by scope, most critical across all hosts, or by host. The reports typically include links to specific details about each vulnerability and how issues can be remediated.
Description.
The screen grab shows the following tabs at the top. Information, results 135 of 1148, hosts 1 of 254, ports 17 of 30, applications 19 of 44, operating systems 1 of 6, CVs 48 of 48, closed CVs 56 of 56, TLS certificates 3 of 5, error messages 2 of 2, and user tags 0. Active or intrusive scanning is generally more adept at detecting a wider array of vulnerabilities in host systems and can notably reduce false positives. A false positive refers to an instance where a scanner or another assessment tool incorrectly identifies a vulnerability. For instance, a vulnerability scan might flag an open port on the firewall as a security risk based on its known use by a certain malware. However, if this port isn't open on the system, unnecessary time and effort is spent researching the issue. If a vulnerability scan throws excessive false positives, there's a risk of disregarding the scans altogether, which could potentially escalate into larger problems. Moreover, one should remain vigilant about the risk of false negatives or potential vulnerabilities that go undetected in a scan. This risk can be counteracted by running repeat scans periodically and employing scanners from different vendors. Automated scan plugins rely on precompiled scripts and may not replicate a skilled and determined hacker's success, potentially leading to a false sense of security. Examining related system and network logs can validate vulnerability reports. Suppose a vulnerability scanner identifies a running process on a Windows machine, labels the application that creates this process unstable, and potentially causes the operating system to lock up and crash other processes and services. A review of the computer's event logs reveals several entries indicating the process has failed over the past few weeks. Additional entries show the subsequent failure of a few other related processes. In this case, a relevant data source has been utilized to confirm the validity of the vulnerability alert. Rate your vulnerability analysis. Vulnerability analysis is critical in supporting several key aspects of an organization's cybersecurity strategy, including prioritization, vulnerability classification, considerations of exposure, organizational impact, and risk tolerance contexts. Prioritization. Vulnerability analysis helps prioritize remediation efforts by identifying the most critical vulnerabilities that pose the most significant risk to an organization. Prioritization is typically based on factors such as the vulnerability severity, the ease of exploitation, and the potential impact of an attack. Prioritizing vulnerabilities helps an organization focus limited resources on addressing the most significant threats first. Classification. Vulnerability analysis aids in vulnerability classification, categorizing vulnerabilities based on their characteristics, such as the type of system or application affected, the nature of the vulnerability, or the potential impact. Classification can help clarify the scope and nature of an organization's threats. Exposure factor. Vulnerability analysis must also consider exposure factors like the accessibility of a vulnerable system or data and environmental factors like the current threat landscape or the specifics of the organization's IT infrastructure. These factors can significantly influence the likelihood of a vulnerability being exploited and directly impact its overall risk level. Exposure factor, EF, represents the extent to which an asset is susceptible to being compromised or impacted by a specific vulnerability, and it helps assess the potential impact or loss that could occur if the vulnerability is exploited. Factors might include weak authentication mechanisms, inadequate network segmentation, or insufficient access control methods. Impacts. Vulnerability analysis assesses the potential organizational impact of vulnerabilities. This could include financial loss, reputational damage, operational disruption, or regulatory penalties. Understanding this impact is crucial for making informed decisions about risk mitigation. Environmental variables. Several environmental variables play a significant role in influencing vulnerability analysis. One of the primary environmental factors is the organization's IT infrastructure, which includes the hardware, software, networks, and systems in use. These components' diversity, complexity, and age can affect the number and types of vulnerabilities present. For instance, legacy systems may have known unpatched vulnerabilities, while new emerging technologies might introduce unknown vulnerabilities. The external threat landscape is another crucial environmental factor. The prevalence of certain types of attacks or the activities of specific threat actors can affect the likelihood of exploitation of particular vulnerabilities. For example, if ransomware attacks are rising within the medical industry, that sector can prioritize those vulnerabilities. The regulatory and compliance environment is another significant factor. Organizations in heavily regulated industries, like healthcare or finance, may need to prioritize vulnerabilities that could lead to sensitive data breaches and result in regulatory penalties. The operational environment, including the organization's workflows, business processes, and usage patterns, can also influence vulnerability analysis. Certain operational practices increase exposure to specific vulnerabilities or affect the potential impact of a successful exploit. Examples include poor patch management practices, lack of rigorous access controls, lack of awareness training, poor configuration management practices, and insufficient application development policies. Risk tolerance. Vulnerability analysis must align with an organization's risk tolerance. Risk tolerance refers to the level of risk an organization is willing to accept. This can vary greatly depending on the organization's size, industry, regulatory environment, and strategic objectives. By aligning vulnerability analysis with risk tolerance, an organization can ensure its vulnerability management efforts align with its overall risk management strategy. Vulnerability response and remediation. Vulnerability response and remediation practices encompass various strategies and tactics, including patching, insurance, segmentation, compensating controls, exceptions, and exemptions, each playing a distinct role in managing and mitigating cybersecurity risks. Remediation practices. Patching is one of the most straightforward and effective remediation practices. It involves applying updates and patches to software or systems to fix known vulnerabilities. Patching helps prevent attackers from exploiting known vulnerabilities, improving an organization's security posture. Robust, centralized patch management processes are essential to ensure patches are applied promptly and consistently. A patch management program focuses on regularly installing software patches to address vulnerabilities and improve security in various types of systems, including operating systems, network devices, routers, switches, and firewalls, databases, web applications, desktop applications, email clients, web browsers, and office productivity applications, and other software applications deployed within an organization's IT environment. Cybersecurity insurance can provide financial protection in case of a security breach resulting from a vulnerability. It is another factor in vulnerability response. While insurance doesn't mitigate vulnerabilities directly, it is important in a comprehensive risk management strategy, complementing technical controls with financial risk transfer. Examples include coverage for data breach response costs, business interruption, ransomware attacks, third-party liability, cyber extortion, and many others. Segmentation involves dividing a network into separate segments to contain potential security breaches. If an attacker exploits a vulnerability and gains access to one segment, they are confined to that segment. This prevents them from moving laterally across the entire network, limiting the impact of a successful attack and supporting incident response teams. Compensating controls refer to measures put in place to mitigate the risk of a vulnerability when security teams cannot directly eliminate it or when direct remediation is not immediately possible. Examples include additional monitoring, secondary authentication mechanisms, or enhanced encryption. Exceptions and exemptions describe scenarios where specific vulnerabilities cannot be remediated due to business criticality, technical constraints, or cost constraints. In these cases, the senior leadership teams accept the risk and document the rationale for the decision along with an established timeline for reassessment. Validation. Validating vulnerability remediation is critically important for several key reasons. Validation ensures that the remediation actions have been implemented correctly and function as intended. Despite best intentions, human error or technical problems can frequently lead to incomplete or incorrect implementation of fixes. These issues go unnoticed without validation, exposing the organization to the same vulnerability it originally sought to address. Validation helps confirm that the remediation has not inadvertently introduced new issues or vulnerabilities. For example, a patch may interfere with other software or systems, or a configuration change could expose new security gaps. Also, validation provides a measure of accountability, ensuring that responsible parties adequately addressed identified vulnerabilities. This is especially important in larger organizations where multiple teams or individuals may be involved in the remediation process. Rescanning and scans after remediation actions have been implemented. The rescan aims to determine if the vulnerabilities identified in the initial scan have been resolved. If the same vulnerabilities are not identified in the re-scan, it strongly indicates that the remediation efforts were successful. Auditing involves an in-depth examination of the remediation process by reviewing the steps taken to address the vulnerability and ensuring they align with the organization's policies and best practices. Audits also verify that necessary documentation has been updated, such as records of identified vulnerabilities, remediation actions taken, and any exceptions or exemptions granted. Verification is the process of confirming the results of the remediation actions and involves various methods, including manual checks, automated testing, or reviews of system logs or other records. Verification ensures that remediation steps have been implemented correctly, function as intended, and do not introduce new issues or vulnerabilities.
Reporting.
Vulnerability reporting is a crucial aspect of vulnerability management and is critical in maintaining an organization's cybersecurity posture. A comprehensive vulnerability report highlights the existing vulnerabilities and ranks them based on their severity and potential impact on the organization's assets, enabling the management to prioritize remediation efforts effectively. The Common Vulnerability Scoring System, CVSS, provides a standardized method for rating the severity of vulnerabilities and includes metrics such as exploitability, impact, and remediation level. By using CVSS, organizations can compare and prioritize vulnerabilities consistently. Another important practice is including information about the potential impact of each vulnerability in the report. This could involve describing the possible outcomes of exploiting of the vulnerability, including data breaches, system outages, or other operational impacts. It is essential to provide recommendations for addressing each vulnerability in the report. Recommendations might suggest specific patches or updates, recommend configuration changes, or identify other mitigation strategies. Timely reporting is also essential, as delays in reporting can lead to delays in remediation and increase the window of opportunity for attackers. Vulnerability reports must use a clear, concise format that is easy for technical and non-technical stakeholders to understand to help ensure that the report is understood and that appropriate actions are taken in response. Rate your Summary. You should be able to summarize types of security assessments, such as vulnerability, threat hunting, and penetration testing. You should also be able to explain general procedures for conducting these assessments. Guidelines for performing vulnerability assessments. Follow these guidelines when you consider the use of security assessments. Identify the procedures and tools that are required to scan for vulnerabilities. This might mean provisioning passive network scanners, active remote or agent-based network scanners, and application or web application scanners. Develop a configuration and maintenance plan to ensure updates to vulnerability and threat feeds. Run scans regularly and review the results to identify false positives and false negatives, using log review and additional CV information to validate results if necessary. Schedule configuration reviews and remediation plans, using CVSS vulnerability criticality to prioritize actions. Consider implementing threat analysis platforms, monitoring advisories and bulletins for new threat sources. Consider implementing penetration testing exercises, ensuring that these are set up with a clear project scope. Rate